So here we are continuing on with alcohols and the reactions of, and on this page we're turning an alcohol into an alkyl chloride, and we see that the alcohol has stereochemistry and the alkyl halide has stereochemistry. So in how we have to work this, we have to be careful what type of reagents we do to make sure we do the right reaction for what's required of the stereochemistry. So we look at the starting material, step one, analyze what it is. We see that we have the alcohol is the oxygen's priority 1, the ethyl is priority 2, the methyl is priority 3, the hydrogen is back, the lowest priority group is in back. So this is S in our stereocenter, and here we flip the lowest priority group and the highest priority group, and the methyl and the ethyl stay the same, so this has to be R. So in this, we have to invert the stereochemistry, so we cannot do an SN1 mechanism here because an SN1 goes through the cation. The cation is planar. The nucleophile will add from both sides. We will not get just the R and enantiomer. We will get the R and S. We'll get racemization occurring, so we have to be careful of that. So since there is stereochemistry involved and it is cleanly inverted in the problem, we have to do an SN2 reaction required. So 1 SN2, because we only invert the stereocenter once. So to do this, we can either do the tosyl chloride and pyridine to make the tosylate, and then sodium chloride, which the chloride would come in from the backside, do an SN2, giving us the inverted alkyl chloride. Or we can do with ethynyl chloride, which will invert it once also. So either of these two ways would work for this reaction to give us the inverted product. But the first way, HCl and zinc chloride, since that prefers an SN1, that would not give us this product. It would give us just the racemized alkyl halide. So what we've talked about so far, and we will continue to talk about, is alcohols can either act as a nucleophile, and if they act as a nucleophile, the oxygen is still in the product, and we do something we add something onto it, like making the tosylate. So here the alcohol acts as a nucleophile, the oxygen is still in the product, and we end up breaking the oxygen-hydrogen bond in the overall process of the reaction. When it's an electrophile, the oxygen is no longer in our product, so it became a leaving group, and we may have to have multiple steps in this to make it an electrophile. We may have to make it a good leaving group and then add the bromide to it. So over the process, we have had the alcohol act as an electrophile, and we have to keep straight which type of thing we are doing, whether we're breaking the carbon-oxygen bond or the oxygen-hydrogen bond. So here we have multiple reactions. We've talked about them, but what do we form in all of these? On the top part, we have the benzyl alcohol reacting with these different things that all form an alkyl halide, whether it be the chloride or the bromide. Now we've drawn the mechanism for these. We know the HBr and the HCl react with the alcohol as if it's an SN1 mechanism. They work best with the tertiary compounds. Thionyl chloride and phosphorus tribromide react best in an SN2 type mechanism. They work best with primary compounds. to make the alkyl halide. So when we see these, we know that depending on what kind of alcohol we have, we can do either the SN1 type reaction or the SN2. Now, starting with benzyl alcohol, it's special in that the alcohol is on that benzylic carbon, so it can undergo either an SN1 or an SN2 reaction. It can undergo an SN2 because the alcohol is on a primary carbon, so we can easily make it a good leaving group and do a displacement on it in SN2 fashion. It is on that benzylic carbon, so we can go through the benzylic cation, and we know that's stable because we can draw lots of resonance structures for that. So we can go through either the SN1 or the SN2 reaction. We can also make the benzyl tosylate, which we'll draw it out once. And the tosylate is a good leaving group, so our nucleophile, whatever it is, can add to that carbon, kicking out the tosylate. So we can make the benzyl bromide, we can make the benzyl cyanide, we can make the benzylamine, we can make toluene, where the nucleophile is just a H minus, or we can make the benzyl ether with whatever our alkoxide is. It doesn't matter. The sodium, remember, in those cases, the sodium is the counterion. It doesn't matter. It doesn't do anything. It's just the counterion for the base we have in solution. So, can we draw an E1 from an alcohol? Well, yeah, we've done that before. We know how to do that. We add a strong acid. It's best to draw it out so we can see the bond we need to take off. We need to protonate the alcohol to make it a good leaving group because the alcohol is not a good leaving group. We can kick it out to make the cation, and then our best base in solution, water, can come in and grab a hydrogen. In this case, it doesn't matter which hydrogen we go for because they're all the same. Pull off a hydrogen to form the alkene, and we've drawn an E1. We can also draw an E1 where the hydrogens we need to take off are different types of hydrogens. We have to decide what can happen in that. In the lower problem, we have sulfuric acid again, and we protonate the alcohol to make the good leaving group. This good leaving group can leave, forming the cation, since it's a tertiary leaving group. And then from this cation, we can take off either the hydrogen in the ring or the hydrogen on the methyl. There are two different types of hydrogens, so we could take off either one. If we take off the one in the ring with our water, we're going to get the hydrogen, or the double bond in the ring, and we know the more substituted the double bond is, the more stable it is. So this double bond has 3 groups off of it, 1 off that carbon and 2 off that carbon, and only 1 hydrogen on it. So it's going to be a more stable alkene than if we redraw this cation and say it's the same cation. And now we could have a water take off this hydrogen to give us the methylene group off of the ring, and we get that, and it has 2 hydrogens on one end, whereas the first compound only had 1 hydrogen on it. So we learned a long time ago that the first compound here is going to be more stable as the alkene. The more stable alkene is the preferred one, unless we have a driving force in the reaction that makes it go to the other alkene. If you had steric hindrance or something in your base. So if we needed to do an E2, in the E1, remember, we formed a cation. The cation can rearrange also if we don't form the most stable cation. So with a cation, we lose a lot of control of the reaction. With an E2, we form our leaving group, and our leaving group can be displaced by having a strong base come in, form the double bond, and kick off the leaving group. And unfortunately, that is drawn wrong to give us the propene. Okay? It don't have 4 carbons in it, so it can't have the isobutylene. So we know that we can do this, and in an E2 elimination, we control the reaction, and it does what we want it to do, and we don't have to worry about other products happening. So what can we do with an alcohol? Okay. We can oxidize it. Okay. Remember what we said about oxidations earlier. If we oxidize something, if we oxidize a carbon, we take it from having a certain, however many bonds to oxygen it had in the starting material, it's going to have more bonds to oxygen in the product. Chromic acid and acetone oxidizes a primary alcohol all the way up to the carboxylic acid. It cannot stop at the aldehyde. We get the carboxylic acid. PCC takes a primary alcohol and makes an aldehyde out of it. It stops before it gets to the acid. So if we made an aldehyde and had more oxidant around that could oxidize it, it would continue on because aldehydes are easily oxidizable. So PCC is an important reagent because it stops at the aldehyde and will not over-oxidize it. Another way to oxidize something is the Swarin oxidation, and the Swarin oxidation will only go up one step. It'll go from the alcohol to the aldehyde or ketone. B and C here stop at the aldehyde or ketone. Okay, it will not over-oxidize that. It won't oxidize a primary alcohol up to the carboxylic acid. Chromic acid goes all the way to the carboxylic acid, or if you have a secondary alcohol, it gives you the ketone. So there's the differences in those, and we have to keep straight which one will do what as we're going along.